Hello everyone, let's get started. In this video, we are going to start the fundamental of continuum mechanics. Then hereafter, we are going to start the continuum mechanics formally, right? In our last video, I have done some exercise questions using our math preliminary. Just watch that video, right? So it will help you to understand the the thing we studied, so how it is applicable to the physics, right? I have done one of the problem here. Okay, so in this video, before directly going into the theory, let me refresh then what you have studied earlier, and also I am trying to uh, give some more in-depth idea of your one-dimensional problem, what you have solved, what you have solved already, right? So in this case, so first of all, in continuum mechanics is a general mechanism. So using this, you can model any type of the material, right? And so far, there are many types of material available in 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 uh, in mechanics uh, in mechanics of material. So let me bring some of the model, right? Some of the basic uh, material model material behavior we define. The first one is the elasticity. Okay, this is very famous. Everybody are familiar in in this model. So what we define uh, as a elasticity, when you apply the load, it stores the energy. When you release the load, it uh, dissipate the whatever the energy it stored. So that means it is completely reversible. Then plus uh, then plus then it is time independent. That means if you apply the load, uh, if you apply the load for uh, longer period, if you keep the load is constant, then the loading behavior also is a constant. It's a time independent. This is called the elasticity. Then there's another model we call viscoelasticity. So we will study viscoelasticity in detail because this is one of the very advanced one of the advanced model in continuum mechanics. We can uh, generalize this viscoelasticity for all type of elasticity problem. Okay, so what we define viscoelasticity, because it has the elasticity mean it still it can reversible but time dependent. So what we define as time dependent. If you apply the load for the certain period, the loading behavior will increase. So for example, you might have studied some of the things called creep and relaxation. Okay, so these two are some of the phenomena. We will discuss later what is creep and everything, but you might have discussed this thing, creep and relaxation, right? So creep mean the deformation we consider uh, with permanent load. The relaxation we consider the loading behavior with permanent strain. We keep the strain constant. We measure the stress in the second case, the relaxation case. In the first case, we keep the stress constant. We measure the strain with time, right? So that is creep. Okay. So no worry, we will discuss later, right? So another one is called plasticity. So what we define as a plasticity, that means deformation is uh, irreversible, right? Irreversible and permanent. Okay, permanent, right? Okay, so this we define as a plasticity. There are many work has conducted regarding this plasticity, viscoelasticity. There are many famous people, for example, Saint Venance, Levy, uh, and von Mises and Duckerberger. There are many people, right? Plandl, Tyler. There are many famous peoples. There are many models available under their names, right? Especially for plasticity. Okay. So these are the type of the material behavior, right? So then by combining these three, these are the very basic fundamental model. Then we can combine these three. We create many models. There's something called hyperelasticity is there. Okay, so then something viscoplasticity. We combine viscosity and plasticity together. Okay, then we elastoplasticity. So there are many models you can develop by combining these three basic models. Okay, so in this case, in next part of the video, I'm going to discuss the something you studied in your strength of material class, the tensile test. For tensile test, you take the material sample like a dog bone sample, something like this. Okay, okay, right, something like this. It's okay. This kind of sample, uh, you apply the tension force by holding these two inside this one. So this is called something called gauge length. So then you measure the extension, then you will get you finally you can uh, plot the stress strain curve, right? Okay. What is this stress strain curve? Initially, in the stress strain curve, let's say this is called there are two stress strain, right? One is stress and strain. Okay. So there are two type of stress. Okay. So one called the nominal stress and true stress, right? So there are something you should know. One is called the nominal stress. Nominal stress. I will write it like this. Okay, I will put like this, right? Stress and strain. Okay, and then another one is called true strain, true stress. Then similarly, nominal strain. Then true strain. Okay, right. So this is something you studied already, right? Okay, right. Then also I defined something else. Then one called uh, L naught. This is the original length. Then A naught. It is original cross section. Okay. So what is original length? The before applying the load, what was this gauge length? That is the original length, right? Okay. So now in the, let's say initially I'll take the example of mild steel. Okay. For mild steel, you know how this graph will come. So initially in mild steel, you will get the linear variation uh, between stress and strain, right? So initially it is just a linear variation. Okay, right. So we'll get this linear variation until one point, right? This point I'll take, uh, okay. So initially till one point, I'll take this point as a double dash, right? Okay. After some point, your graph will become that initially it will be the straight line, the linear variation. After that, it will become slightly non-linear till one point, right? Okay. So this point we define as a dash, right? Okay. Then after that, you will see a small drop here. Okay. Small drop here. Then there will be oscillation, something like this. Then you will reach one point. This point I will call as a B. Okay. So this is kind of a oscillation here, right? So after that, after the reach this point, then uh, the material follow the nonlinear behavior variation like this, right? It will go to the ultimate point, then it it reached the decline region. So because of the necking, something like this, right? Because you will get the necking. When the necking is take place, this stress will decline, right? So okay, here let me mark one point here. Okay, so this is something called U, right? Okay, U will be the maximum point, right? Let me mark here U. Okay, so it is the ultimate point, right? Okay. Uh, so this one, let me mark this point as A, right? Okay. I think I have marked everything. So let me check with my notes whether I marked the same things because I have to give the lot of points here, important points. Okay, right. So here, let me mark one by one, right? Then A double dash, okay, we called as uh, proportional limit, right? Okay, so let's say here it's A. Within this OA double dash, in this case, this region, you can apply your Hooke's law, right? Okay. Then the A dash we are calling as uh, upper yield point. So that means there is it will go, there's a drop here, the vertical small drop. That's what A is upper uh, yield point. Then your A we define as initial yield point, right? So this is what we called as initial yield point. This we define as a yield point. Really, if you are saying the mild steel yield strength, we denote with A, not A dash, right? Initial yield point. Okay, so this is actually the onset of yielding, right? Initial yielding. Okay, the initial yielding, there is an onset, right? Okay, so then uh, the B, right? The region AB, the region AB we define as the within this region, the stress is a constant, right? Stress is a constant. Okay, so therefore here it is called uh, perfectly a plastic behavior, right? So why we define as a perfectly plastic behavior in this region, right? The stress constant, then strain it's increasing, right? So that's what we define that one as a perfectly plastic region, right? Okay. Uh, right. Mm, okay. Here, everything I have point out, I think I have marked here. The another one is uh, in the the point A. This point A is the initial point. Then A we are taking as in for the real design. Okay, A we consider as a that means lower yield point. It is the lower yield point. Yield point, right? So this is the one we have taken as elastic limit, right? Chosen as elastic limit. In other word, it is called yield stress, right? Okay, right. So then U, I have to mark the U, right? U we define as ultimate stress, right? Or ultimate point. So if I say point mean, I am actually representing the stress, right? Okay. Okay. Then there are some name. The region ABU. Okay. So before that, let me mark BU, right? Okay, I'll put here the BU we define as uh, material hardening, right? The region we are calling as material hardening. So in other words, sometimes work hardening, right? What we define as a work hardening and material hardening, in this region, for small stress, you can deform the material in with large strain. Okay, you can easily deform the material but with small stress increment. So if you small stress increment, you can increase the strain very large value, right? So that is what we define this one uh, as a strain hardening, right? Then also within this region ABU, right? ABU, actually here uh, material is plastically deformed, right? Deforming. Okay, Material is plastically deforming. Right. Okay. This is something you studied earlier. Just I uh, refresh what you have discussed in your previous cases, right? Now, what is the important things you should know here? Uh, if you let's say you are moving here. Let's say you are coming to one point. Let's say one point, this point G. At this point, if you remove the load, it never go to the previous original shape, right? That means previously, for example, within this region, within this A, even if you are loading, if you remove the load before this reaching A dash, the material will follow the same position again. Okay, so that means within this region. But in case of here, when it is passing the that means material hardening region, in this region, if you remove the load here, material will never come to the same position. Then it will come to uh, the different position, right? Different shape. It has some permanent deformation here, right? So this we define as uh, film P. So this is we called as a permanent deformation, right? Plastic strain or permanent strain, right? So that means here this is we called as plastic strain or permanent strain. Okay, right. So now let's say now your material is here. If you load the material again, material will follow this line, this path again. Let's say if you remove the load, unload at this point, again material will come to the same position again. Okay, clear? So that means it is going here, coming here before reaching point E. So therefore, this part, right, this portion, okay, this portion, okay, this portion we define as this portion, right? Elastic strain, right? So that means it is the recoverable strain, right? Okay, this is elastic strain, right? Okay, then this one is total strain, right? Okay, so now let's say, uh, okay, I'll mark like this, right? This point I'll take as a D, this point is I'll take as G, right? Okay, so now before reaching this point G, material will come to the same position, right? Once the material reach G, again, as previous case, you will get again the same, what you call, same as like this, the nonlinear deformation, right? Okay, so it is like this, right? Uh, okay, it like this. Then it will reach this point, the previous curve. Let's say this point is H. Then from H, it will continue again the previous curve, right? Okay, right? This phenomena will happen again. For example, if you remove the load at H, then it will, if you remove the load at H, then it will come to the different position. Again, the same thing what I already explained will happen for new line, what we have drawn. Okay, so here the point H, Um, the point H is something like as previous, right? G is uh, proportional limit, the second proportional limit. H is the uh, subsequent yield, right? Subsequent yielding. Okay, right. Okay, H we called as a subsequent yield point. G and H again we, okay, so G we called as subsequent yielding, right? Let me mark that one. G sub subsequent yielding. Okay, so you know the total strain, it is actually elastic strain plus plastic strain, right? Okay, right. This is for mild steel case, right? Steel case. Then there's another type of material is there that is for okay, let me bring this one to another next page. Okay, it is here. So now let's say you have something. What the hell? Okay. Uh, you will have sometime some material, let's say like aluminium. So in case of the aluminium, let's say aluminium. So in this case, your stress strain curve, you won't get like this AB, that means this yield point, visible yield point. Then in that case, you will get the curve something like this, right? You will get initially here, so like this, then it's continuously, it come like this, right? So again here you have the yield point U. Okay, as similarly the previous case, right? So this is called the ultimate U. Then uh, the problem is here, you cannot identify the yield point here. So therefore what we do here, we draw a 2 percentage, right? That means 0.2 percentage offset line here, right? This is because here we cannot define the yield point accurately. So therefore, in this case, we use something called this strain. This is called reference strain, right? So what we do, sigma r normally 0.2 percentage of the initial length. We draw the parallel line to initial slope here. This point we define as our yield point A. Okay. Then similar to like that, we will get the same D point D here. Okay. If we remove the load at point D, then it will come to the permanent deformation, right? Okay. The permanent deformation, this point, did I mark anything? Okay, let's say this is E, right? The same point E you will get here. Then the similar to the point G you will get here. Okay, so let's say point G. From point G, again, you will get the similar situation. So this is your point H, right? as similar to the previous case. Only different is we find the yield point because this yielding is not visible here. So therefore we find the yield point at this case, right? Okay. So this is your point D, right? The similar to previous case, right? Okay. This is in case of aluminum. Okay. All right. So here I'm going to tell you some of the important things. The first one, your nominal stress. Nominal stress mean your engineering stress, another word, right? Now, what we define as a nominal stress, the force, applied force, right, over original cross section, right? Cross sectional area A naught. I'm talking about the nominal stress. So this is something you studied. This is the one you studied as a engineering stress. Okay, nominal stress or engineering stress. Similarly, nominal strain, what we define as force divided by original length, L naught. These two, that mean no nominal stress and nominal strain, is the one I have drawn here in both cases. Let's say someone can keep the force as P instead of A naught because the material get elongated, the cross-sectional shape, cross-section will vary, right? If someone used the cross-section at the time of the load apply, original cross, not instead of original cross-section, if we use the uh, uh, the true section, true cross-section, in that case, we will get true strain, right? Sigma I define as a true strain. Just remember this thing. Okay, let me bring this one again there. Okay. Okay, you won't get confused. Okay. Okay. So that means these things I am defining now. Okay. So that is true stress. Similarly, you can define true strain P over L now instead of L naught. Okay. So this is we define as true strain. Okay. Again, true stress and true strain. Let's talk about true strain. True strain we don't define for large element because of we are considering the changes of the length. So we normally we defining at the infinitesimal, very small length. That means we define something like this, right? D epsilon. So I d- okay, I cannot have P here. This is the extension, E. Okay, E over L, right? Extension over L, right? Not P, E. Okay, E is the extension, right? So here that change in length, right? That change in length I'll take as a DL. Then here it is original length L. Okay, so I have defined this one for true strain for actual case, right? Let, let's see. Now, what I'm going to do, I'm going to find the total strain, right? So this is like I define for the total strain, but I cannot define something like this for the true strain, right? So this is actually the true strain I have defined for infinitesimal length, right? So now if I want to find the total strain, you have to integrate, right? If you integrate this side, you will get strain. So this is something like integration of dl over L. Okay, this is something right? So that means, let's say if I integrate this one with the limit, okay, with the limit from L naught to L, okay. So integration of this one, L and L, So L naught to L. So that means ln L minus ln L naught. So this is, you can write ln L over L naught, right? Okay. So this is something very important. Your true strain is ln L over L naught. What we define as L, let's say this is your uh, initial length, then it increase, this length increase by dl, right? Okay, so this is your L naught, right? So this is your L. Okay, so actually the true strain we define with L, right? Okay, so therefore this L you can write like L naught plus this extension, right? This extension, let's take this is E. Okay, let's take this is E. Okay, E over L naught, right? Okay, so that means L equal L naught plus E, right? Okay. So now ln, okay, uh, this is, you can write 1 plus E over L naught, right? So from here you can write epsilon true strain ln 1 plus E over L naught, that is actually your uh, nominal strain, right? Okay, so this is very important, right? Very important relationship between true strain and nominal strain, right? Okay, so let's say this is equation number one. Okay, because I'm going to do a lot of calculation here, right? That's what. Okay, so this is something, the relationship between nominal strain and the true strain, right? Similarly, I'm going to find the relationship between the nominal stress and true stress, right? Okay, this is something very important because to find the relationship between nominal stress and true stress, we take one assumption. This must be very careful. This assumption you must understand because I have seen uh, many papers, right, in finite element papers, uh, even for the researchers level, right? Uh, in if someone use abacus or ANSYS, right? In abacus, for finite element software, we we use true stress and true strain for the material model. Let's say if you run an experimental study, if you want to uh, define the material property as a stress strain relationship in abacus, you have to define true stress and true strain. Okay, but true strain, no problem, because here we don't take any assumption. True stress, we are taking a following assumption. The assumption is we assume incompressibility. Material is incompressible. Okay, this assumption we are taking. Okay, assumed incompressible. Incompressible. Okay, okay. We assume this one. This assumption we are taking for true stress, nominal stress conversion. Why I am saying this is importantly, I have seen many of the research paper in finite element study. They have done the finite element study for compressible cases, but they have done the abacus analysis using the relationship what I am going to derive now. But they assume incompressible, but they are doing the research for compressible cases, right? It is completely rubbish. Okay, so there are many papers, right? Because why I'm saying even in this part they are missing in even the high research committee also, they don't consider this part carefully. They don't treat this one is very carefully. What we define as a incompressible. Incompressible mean no volume change. No volume change. The volume is equal. That means the initial volume. What is initial volume? Initial cross section and initial length equal final cross section and final length. Okay, so now if I take true stress, that means force divided by true area, final area. Okay, so now P, instead of A, from here I can find A is equal A naught L naught over L, right? So therefore, instead of A, I can substitute this one, right? I will put L naught here. The L will come out, right? L over L naught, right? Okay. So now this P over A, that is actually our nominal stress, right? P over A naught. It's a nominal stress. What is L over L naught? L over L naught, L over L naught, we already derive 1 plus E over L naught, right? So that means 1 plus uh, true strain, right? Sorry, nominal strain, right? 1 plus nominal strain. Okay. So this is the another important equation. That means true stress equal nominal stress into 1 plus nominal strain. Again, the second equation with the condition of incompressibility. It is very, very, very important. If it is not incompressible, how we are calculating this one? Okay, that is I will tell later, right? Keep it in mind, right? Okay, right. So this is the next point, right? Okay. Uh, so now the important thing is true stress keep on increasing until material fail. So for example, the nominal stress here, you see when it is reached one point, it decrease, it reduce, it's decline. Why? Actually the cross section necking, cross section is reducing, actual cross section, but we are converting this one with the previous cross section. So that is what the force is reducing. So that is what the the nominal stress is reducing here. Okay. But if you plot this one in the true stress, it is actually the increasing. It will increase from this point, right? So until point D, it is same. Why it is same? Because the cross section change, it's not much significant. After reaching point D, I told you, after that the necking will take place. So therefore, there's a large reduction in initial cross section and the final cross sections. So therefore, after this point, there will be significant difference between true stress and nominal stress, right? So if you plot true stress here, the graph will be like this, right? Okay. So graph will be like this. Okay. So now this will be your U dash. This is your true stress, right? This is for true stress. Okay. Similarly here, so this is the true stress at this point, right? So here, this will be the true stress. Okay. So what is the one point you must understand here? The true stress keep increase, right? That means true stress, true stress uh, keeps increasing until material fails. Okay, so this is very important. Why it's true stress continuously increasing? That's what I am going to tell next. Okay, um, let's say one by one, right? Uh, okay, so let me write the first equation, right? First equation we already derived. Your so that means true strain is ln 1 plus nominal strain, right? Okay. So this is if we convert, it is E, right? If we convert to normal, that means 1 plus nominal stress equal exponential this one, right? Okay. This is something you know, right? Simple mathematics, right? So therefore from here, you know your nominal strain equal minus 1, right? Okay. So these are the important point I'm going to tell you, right? The third one. Okay, I'll mark this one as equation number 3. Uh, okay, so there are many things in coming my mind. Okay, okay, I don't want to go to that direction now. Uh, let me explain this one first. Then later I will explain that part, right? Okay, so now similarly from equation number 2, uh, your what we define this one, right? So that means your true stress equal nominal stress into 1 plus nominal strain, right? So 1 plus nominal strain, 1 plus nominal strain, actually this one, right? Exponential true strain, right? So therefore here, this one, sorry, this one exponential true strain, right? Okay. So let me take this one as number 4, right? Okay. So now what I'm going to do, this number 4, I'm going to find now the variable is strain, right? Okay. So now I'm going to uh, differentiate this one with nominal strain, right? Why I'm going to find nominal strain, I'll tell you, right? So that means this one I'm going to differentiate with respect to nominal strain. Okay. So this equal now uh, mm, how can I write this one, right? Okay, here. Okay. Hmm. Okay, I will write it this way first, right? The fourth equation, I will do like this, right? Okay, what I am going to do, I will do, I will take nominal stress equal uh, 2 strain into, if I take it this one another side, I can write like this, right? Okay, right. So now I'll take this is number 4, right? But mean because 3 and 4, now I am taking for nominal stress and strain, right? So now 4, I can write nominal stress. I'm going to differentiate with respect to nominal strain. So what is this one now? I am trying to find the slope of this curve, right? This is nominal stress and nominal strain. Slope of this curve. Okay, right? I am finding slope of this curve. Okay. from equation number 4. So now what is that? This is like now uh, uh, okay. Uh, okay. Now if I want to find this one directly here, so now from equation 4 is the variable is epsilon, right? So I can apply the chain rule, right? So that means d epsilon dot chain rule, right? Okay. In this way only I can find here, because the number 4, the variable is true strain, right? So therefore first I want to differentiate with respect to true strain, then true strain and nominal strain differentiation separately we have to calculate, right? So this one now, then now I'm going to write the right side part. Right side part, what is that? Uh, it is something like UV form, right? Okay. So that means keep sigma, differentiate this one, right? E to the power minus, then minus, right? Plus, then keep this one, differentiate this, right? Then mean uh, with respect to uh, this one, right? Epsilon. Okay, keep this one, right? Keep E minus epsilon, right? So now, okay, into, so now what is that? I have differentiate this one with respect to epsilon, then this one, I have to differentiate this one, right? Okay, right? Okay, so that means this is actually this one, right? Okay, right. So this is remind this one, right? Okay. So now this part I can calculate from third, right? Equation. Now I'll take this is equation number 5. Equation number 3, I can calculate this one, right? From equation number 3, I can calculate from equation number 3, I can calculate uh, d epsilon df. Okay, so now here this one, right? So therefore d epsilon over this one. Okay, so this will be interchange. That means e to the minus epsilon, right? What is e to the minus epsilon? Now I can write like from here, from here, e to the minus of 1 over this one, right? So I will write 1 over e to the epsilon. That means 1 over 1 plus this one, right? I'll take this is equation number 6, right? Okay. Now I can write from 5 and 6. So now I can write this one equal uh, mm, or else I'll keep okay, I'll keep this one, right? This is I'll keep this one only, right? Okay. I think I'm confusing a lot. It's not confused. Just I'm keeping this one, right? Because simply we can simplify, because here also we have e to the minus epsilon is there, right? You can take it out, right? So therefore in the equation number 5 I will write this part first, right? E to the minus epsilon I'll take out, right? So that means d sigma over d epsilon minus sigma. If I take e to the minus epsilon, so this is already we derived, that is e to the minus epsilon. There is another e to the minus epsilon. If I take this one, it will become e to the minus 2 epsilon, right? Okay. This is equation number 7. Now, So very important, right? So now what I'm going to do, uh, so what is happening here, right? If you want to find whether the function, whether it is increasing or decreasing function, you have to find this sign, right? If it is increasing or decrease function, you have to show this one greater than equal to zero, right? Okay. If you consider this one, you see in the nominal stress slope in the diagram, you remember it is positive zero, right? So that is the case, right? In most of the cases. For example, let's say in case, let's say if it is zero, okay, let's say where it is the slope becomes zero. So that means it is ultimate point, right? If it is zero mean this portion is zero, this portion is zero. Because this is cannot be the zero, exponential not a zero. This portion is zero, in this case, d d epsilon equal this one, right? You will get this one. So what is the meaning of this? This is actually the slope of true stress, true strain curve, right? What is the meaning of true stress, true strain curve? In this true stress, true strain curve, this is sigma. Sigma, always positive. Sigma, so that means sigma always positive, right? Okay. So if you don't apply the load, it's zero. In other case, it is positive, right? So that means d sigma d epsilon always greater than rho. That means always the slope is positive. Therefore, slope positive mean you never get like decline portion, right? Always is an increasing portion you will get. So that is what I told you. True stress keep on increasing, okay, until material fail. It never come to the decline portion. Why? That reason is the one I told. This is what we told. True stress keeps increasing, right? Until, okay, until material fail. Material fails. Okay, right. So I hope this is clear, right? Because actually I have used some here and there, but anyhow, the finally I managed. So just you can go through the video again and check what is happening here. Very important point I am telling you, right? Okay. Now, right. Okay. So to end up this video, I will tell you one more things, right? Okay. One more things. Okay. Okay, right. So before that, you remember uh, our equation number three, right? Equation number three. What is equation number three? This one, right? The pin. That means nominal strain equal e to the power true strain minus one. We studied something in Taylor series, right? In Taylor series, we studied this one, right? X squared 2 factorial, x cube 3 factorial, something like this, right? So therefore, if you write epsilon minus 1, that means true strain in terms of, that means nominal strain in terms of the true strain, you can write like this, right? E x minus 1, therefore this minus 1 you can take another side. So here you will get this one, right? Epsilon squared over 2 factorial, 3 factorial. So like that it will go, right? Okay, then finally if you consider the nth term, Okay, n factorial, right? So like that it go. Okay, so now this is very important. If you eliminate the order of 2 as 0, what is that? Your true strain and normal strain is equal, right? So this is only at higher order terms eliminated. That means small strain case, right? So this is the thing you studied in your strength of material class. In the strength of material, you studied, you never differentiate these two, right? True strain and normal strain. Because that is, you studied under this assumption, small strain assumption. Okay? So there, the difference between true strain and normal strain, you can ignore. Again, this is for one dimension case I am telling, right? We will derive this one for two dimension case, that means general case, the next video. But for the moment, you understand what is the meaning of this small strain assumption, right? Okay, right. Uh, okay, so in addition to this, there's a one more thing you must understand. The true strain is additive, not but no nominal strain is not, right? But nominal strain is not. What does this mean, additive? For example, let's say you are taking the original length L naught, then you uh, increase to length L1, then you increase to L2, the length. Okay. So let's say if you want to write true strain, let's say in this case, the first case, epsilon 1, you can write true strain, the equation we studied, L1, L naught, right? This is something we studied, right? Uh, we just derive, right? So that means this one, right? True strain, Ln, L over L naught, right? So now here, my final length is L1, initial length L naught, right? Similarly, the second case, epsilon 2, if I this case, if I take the strain and the second case, it will be Ln, okay, Ln L2 over L1. Why now L1? Because I am taking the strain for second case. For second case, the initial length is L1, right? Okay, right. Okay, so now if I calculate the total strain, that means sigma 1 plus sigma 2. In this case, Ln L1 over L naught plus Ln L2 over L1, right? So now you know the log function, if you take Ln as a common, this will multiply, right? So that means L1 over L naught multiply uh, L2 over L1, right? Now these two cancel out, right? So that means Ln L2 over L naught. So this is the meaning of additive. That means if I write directly the final stage, the total strain, the same thing I will get, right? That means intermediate strain, if I sum up the intermediate strain, I will get the total strain for in case of the true strain. But in case of nominal strain, what is sigma 1? Sigma 1, it is actually L1 minus L naught over L naught, right? Okay, right? Then sigma 2, L2 extension is L naught, right? Okay. what is the length you have to use? Original length is still L naught. So if you take the total strain, what is that? L2 minus L naught over L naught, right? So that means total strain is actually sigma 2. It is not additive, right? Okay. So that means you cannot get the additive. It's not additive. Individual strain, if you sum up with, you won't get the total nominal strain. This is the problem of nominal strain. But the true strain is this one. That is what in finite element software like Abacus, okay, we use the true stress and true strain because it is additive. It's easily apply for the numerical application, right? Okay, I think this video bit extended, no issue, but we have discussed a lot of important stuffs. Again, if you do not subscribe my video, please subscribe and share among others. Please like the video, right? Okay. Okay, I will see you in next video.